Hi everyone, it's my pleasure to introduce Ivan Cheltsov from Edinburgh. Who's going to tell us about which real cubic are rational.
Thank you. Yeah. It's very big pleasure to speak about rationality of cubic frequency. So let me start from reminding few classical results. So first I start considering all complex numbers. So if we have a cubic threefold in P4 and if it's smooth, then it's irrational. Yes, and this is famous result of Clemens and Griffiths. Okay, and this covers, so this result on its own can be applied to many other actually algebraic varieties. So basically this is Fana and Fana variety, Fana threefold. And the rationality problem for them is super classical. This is the first result, deep result in this direction. But actually, one can apply it together with the degeneration technique. So basically, if you have, for example, family, for example, one-dimensional family, Fana varieties with mild singularities. For example, Fana threefold, but for simplicity, with mild singularities. Or singularities. Then if, for example, central fiber is irrational, if it's irrational, this implies that very general fiber is also irrational. For very general T. And this, together with this, very applicable. So, for example, let me give you an example. It's a work in progress. So don't do this. Finish. Work in progress with Takuza Akada from Kyushu. So if you consider hypersurface and weighted projective space, such that weights are ordered and such that degree is sum of weights minus 1. So this is Fana. And let's assume singularities are mild. Let's consider two assumptions. So first of all, in order for this to be Fana, we have to assume everything is well formed. So for example, that any four weights here are prime, and if you have the dimension 2 singular locus of weighted projective space, it's actually not contained in X4, so we assume it's well formed. And we also assume it's that's quasi-smooth. It means if you take a affine equation of the cone, it's smooth away from the origin. Okay, then these two conditions imply that you have 4,442 sporadic possibilities for the weights. For weights. weights 5, or around 15 infinite favors, or 15 infinite series, one parameter series. So this is was done by Janusz and his wife, Jennifer, long time ago. So Takuza and me, we decided actually to prepare a test object for new theory of Ludmil and his friends in order to test rationality. So, for example, if you've been like in some conferences organized by Ludmil, you know that there is a big activity of atoms, theory of atoms, to prove new variational invariance. They want to apply it to many cases, but usually what they want to apply to Fano threefolds, to Fano fourfolds and high dimensional arrays, which they want to apply, we sort of expect that all of them is irrational. So if they apply the technique, they say, okay, this guy is irrational, but we all kind of expect
a general one.
General one, but almost some. For example, they also can apply, say, to smooth cubic threefolds or some other objects, but we expect that they're irrational. But what we wanted to do with Takuza, we decided to take all of these guys. This is thousands of families, and just to check which one are rational or irrational traditional technique, also general member. And but in this case, situation is not like all of them are irrational. So basically, what we proved so far, I mean, there's unfinished things. So here, general member is always irrational. So this is infinite many families. So general member is irrational. But here, it was kind of surprised. So far we have around 1,000 rationals and around 1,500 irrational and other work in progress. So, and it's really, you cannot, if you look for the weight, for given weights and given like degree, sometimes it's absolutely unpredictable which one is rational or irrational. You really have to work on geometry. So this is, I think, it's a very nice, like a test field for theory of atoms in the future when it's going to be generalized for orbifolds because it's singular. So far, the theory is smooth. But what I want to say that rationality is always done by some explicit construction, but irrationality of all of them, of thousands of families, irrationality always done using this theory. So, not by one, you basically get some general degeneration. You have degeneration construction, and you degenerate to smooth cubic threefolds. And then you put some condition on the weights in order this degeneration construction works. Then you run some small program and it give you like hundreds of weights each, okay. And then you hook up another degeneration, something like that. So it's you can say it's like one by one with a computer. Yeah. But surprisingly, all irrationality results here obtained using this result. So it's very powerful. And the reason is that if you put like kind of take Fano threefolds, like in general, yeah, if you put this as kind of irrationality scale, so if for example here is a rational, so here is something like very non-rational. For example, I didn't mention yet, but it's classical theory by Miskovsky and Manin. If you take smooth quartic threefold MP4, it's also irrational by Miskovsky and Manin, but this is very, very irrational. So cubic is very close here. So it's very close to rationality. So for example, it's very difficult to apply irrationality of quartic threefold using degeneration, because very few functions going to degenerate to this. But to this, a lot, really a lot. For example, even the quartic, you can easily degenerate to a cubic in a hyperplane. Yeah. So this result is very powerful. And and together with the degeneration construction. So
It's like, no, is there something even more close to rational? That's irrational. We put the x.
no, x3. I mean, this is okay. Irrational is somewhere here. Rational here.
Yeah, so is there something even closer in your scale?
Closer?
Yes.
There's nothing. There's nothing closer to I mean, it's very hard. I mean, this is more or less intuitive, but it's not exactly intuitive. It's from the point of view of degeneration. If it's something closer, it means you can degenerate to this guy. Yeah, but and we see the reason. Yeah, no matter how you degenerate this, you get a rational one. This is it sounds the topic of my talk. So you can ask the question: okay, what if you degenerate cubic threefold? You get singular cubic threefold, and all of them are rational. Yeah, so just observation. So if you take cubic threefold P4, if it's singular, then this is rational, except one strange case when it's a cone over the cubic curve, but which is not very interesting. Yeah, so in particular, singularities like isolated is definitely rational.
So I apologize. What's written on the second?
You know what written. So basically, this project originated long time ago here during some reception. So basically, Emil was explaining me what he's working with Maxim, with Tony.
Let's tell me about the history. What's written?
Written is this: the scholar Johnson hypersurface.
Okay.
And I said we have
Dimension 3.
dimension 3. All of them, by the way, all of them out of this huge list, only 2 families contain smooth members. One is a quartic in P4, because I assume this condition, and another is sextic in P11112. This families contain smooth members. All others are singular. All of them are singular. But singularities are mild, like quotient singularities, basically cyclic quotient singularities.
So these two are birational.
These 2 birational relations. Yeah. But okay, so basically I explain what during the reception. Yeah. Okay. So if you consider cubic threefold singular, it's rational unless it is a cone over elliptic curve. Okay, so nothing interesting. But if you consider now the problem of arbitrary field, say for simplicity, let's keep it characteristic 0, but not algebraically closed. Then we don't know the answer for rationality question. So if you consider cubic threefolds singular with any singularity, for simplicity, we assume to start with the simplest possible singularities, ordinary double points. If our field is algebraically not closed, that we don't have an answer in general. I mean, you have some obvious conditions, but we don't have answer in general. So maybe like last year, together with Yuri Tschinkel and Zhijia, who is here, we decided to consider this problem over R. Just real, so in some sense, like historical. For most of people, it's like non-mathematicians, it's easy to
Because this is the simplest group you can get.
Okay, if you want to really reason why we did this. So before this, we consider cubics over C, but with a group action. And you can consider the problem of equivariant rationality. So we know, for example, if you have over complex numbers, you have algebraic closed field. If cubic is singular, it's rational. What does it mean? It means there exists a birational map to P3. But then you ask the question, do you have equivariant birational map like this? And the answer is maybe yes, maybe no. So this problem is, in some sense, similar to this problem, but here is a Galois group action, and here is a geometric group action. But this problem is much more accessible. Why? Because you can basically, what actually we did, you can go through all possible singular cubic threefolds, and you can describe all the automorphisms. Of course, you don't need all. For example, if group fix a point, singular point, then projecting from the point give you equivariant rationality construction. So you don't need to consider groups like this. For them, you know the answer. So basically, we consider groups which are does not preserve any singular point, and we more or less, it was series of 2 papers, also with Yuri, with Zhijia, and this one paper and second paper with also together with Lisa Markon, with a postdoc in NYU. And we didn't solve this problem completely, but we solved a lot of cases. We found all possible groups which can appear in this case, and cases which are open, they're very explicit. Cases where we don't know the answer, here we have equation of the cubic and we have a group action. And I say, okay, we don't know answer here, but it's very kind of easy to start working on this problem because everything is explicitly given. So this problem is explicit manifestation of this problem. Here, it's more difficult, I think. So, but when we went through this equivariant problem, of course, a big part of the group was involutions. Yeah, and then we realized that a lot of this construction can be applied here to the Galois group action. This is how we said it. But also because it's kind of, okay, because it's R, immediately there's some, yeah, because maybe, okay, it's kind of very kind of nice and some from historical point of view.
I mean, actually, from my really limited experience, usually it is the hardest case.
It is the hardest case. Yeah, it is the hardest case. But also, it depends what you want. Also, from some point of view, you have a lot of rationality construction of this case. So from this point of view, it's maybe not so hard. Okay, I must say that we were not the first who consider rationality problem for funness of a non-closed field. And recently, very recently, last few years, there was a lot of papers on the subject by Kuznetsov, Prokhorov, Benoit, Wittenberg, Yuri, Tschinkel, Brandenhauser. There was many results. So in general, so you can
What the French people?
Olivier Benoit and Olivier Wittenberg.
Wittenberg.
Yeah. So basically, recently, there was the progress on rationality of smooth funness threefolds over non-closed fields. Over non-closed fields, characteristic 0. Including with a special emphasis on the real field, including the case R. So this problem, okay, let me remind you that we have 105 deformation families of smooth funness threefolds. Okay, usually labeled like, say, 1, 1, 1, 2, yeah. So this is Picard rank of Picard, and this is just a number. Yeah, so for example, this is 1, 2. Yeah. In cubic, I think it's like 1, 12. So what basically, well, this problem is still not completely solved, but it is more or less,
Cubic is 113.
113, okay. More or less solved for Picard rank, geometric Picard rank 1. And also mostly solved when, this is basically paper by, this is Kuznetsov, Prokhorov, big paper. And also with, as I said, Benoit, Wittenberg, and Brendan, Tschinkel, and very few more people. And also the case when Picard over non-closed field, also Z. Yeah, but there's also cases when Picard group over non-closed field when it's also larger than Z, and some of these cases not yet solved. So, but there's a lot of, we have a, for smooth case, we have a very clear picture what's going on. Let me just give you examples, something which is not yet done. Example, this is in a paper by Kuznetsov, second paper by Kuznetsov Prokhorov on this topic. So just examples of, suppose you consider divisor in P1 to the fourth of degree 1, 1, 1, 1. Okay. And smooth. Yeah, and you consider form of this divisor. So, okay, you consider, say, some K form of this divisor of Picard rank 1. And in this case, what we know that there are fields on which very general member of very general threefolds with this property are irrational, using the generation technique actually to the toric one. But in general, if you like fix the field, for example, if you take a field to be real, we don't know. And they put as a conjecture in the paper. So then this form is always irrational over the base field. Yeah, over the base field. But it's widely open. So
Let me understand that. So this is, we have a group action which is transitive.
yeah, basically equivariant setting. You have a group which permutes transitively factors here. And equivalently, it's very easy to produce examples that is irrational.
So it's basically it's something that group which suggests on the form action.
Yeah. No, not necessarily. It can be actually Z mod 2Z square. Example can produce this example.
But in this case, it's still not known.
No, it's not. Okay.
I mean, I just want to know.
For smooth one, no, it doesn't know.
What about if it's only Z2?
This is one of these cases I will mention. Not know. Z2 don't know.
So I'm just asking so that I know what I should talk about.
Okay. If it's Z mod 2Z, like in our case, if it's say permute this two factors, 2 and 2, then we actually don't even know what to expect. Because we don't have examples, we don't have counter examples. So I don't know. And I think, yeah, Zhijia, do we have intuition? We discussed with Yuri, and we didn't even intuitively don't know what the answer should be in this case. So it's probably also irrational. Okay, anyway. So let me briefly summarize what we did here. so this was last year. We didn't solve this problem, but we explicitly listed cases where we don't know the answer, cases very explicit. Let me just summarize what's done about real cubics. And
There are two questions here actually. So when you say 105, how do you know that?
this? Okay, it's a question to Mori and Mukai.
But but isn't there a work of a ratio that with using quantum is good?
For smooth
The
ones?
smooth guys, it's the classical result.
Okay, so
Well,
first of all, in the classical result, there was a mistake. We missed one family.
When I was an undergraduate student, there were 103.
104.
No.
Even three.
Umemura was
No. Okay. No. Okay, if you want this history, story is like this. Iskowskich was working on Picard group Z case, and Mori and Mukai was working on a higher Picard case. So Iskowskich really needed to know few things about Picard rank 1. First, he have to know that each such threefold contains a line. In line means curve intersect minus k by 1. So if it's minus k is very ample, it's a line. So Iskowskich basically, in the beginning of his study, he just put it as a conjecture. It was a conjecture about the line. But later, after Iskowskich actually got classification, it was proved by Shakur. Only after Iskowskich got the result. So Iskowskich put this as a conjecture. So it was
by Mori and all.
Wait a minute. Second conjecture was that anti-canonical surface is general one, smooth, which also was proved by Shakur. And
Shakur proof also had some problems. Okay.
Yeah, later removed by mile 3. Yeah, this is also
mile 3 proof has problems. It's been fixed by Tanaka's theory.
Yeah, true. This is also true. Okay, I didn't want to say about this, but this is also true. But then Iskowskich also had a lemma. He proved basically that if you take a Hilbert scheme of lines, it's always reduced. And this was a problem. He proved this and he got classification, and then Shakurov proved this result. But then Mukai and Umemura, they constructed example of smooth final threefolds of degree 22, x22, which is based, I think it's like 1, I don't remember, 10 or something like this. Which actually, so this usually denoted this Mukai and Umemura, such that scheme of lines, it's a multiple conic. It's not reduced. And it basically means properties of the normal bundle. If point on the Hilbert scheme is singular, its normal bundle is special, not very balanced. And Iskowskich really needed this normal bundle to be good. So basically, yeah, but then Mukai and Umemura, when they constructed this example, Iskowskich immediately asked his former PhD student, Yuri, to sort out these cases, and Prokhorov explicitly proved that this is the only example when the Hilbert scheme of lines not reduced. So basically, Iskowskich didn't miss a family. He missed a one threefold in six-dimensional family. So it's not exactly one threefold, just one threefold. It's okay.
You are a subject of Her Majesty. Let me tell you the story which I know from the subject of Her Majesty. Apparently, this variety was discovered by physicists because it's a twistor space. And they look at the list of classification. They prove that the twistor space must be found. And they actually couldn't discover the twistor space of a K3 surface in the list of classifications found. This was Kitchen and
okay.
So that's how it was discovered.
Okay, so yeah, but indeed, in the Mori Mukai, they use MMP, basically, classification of extremal rays by Mori, to study Fana varieties with higher Picard. Because if Fana variety has Picard rank 1, there's basically no MMP. So you already stopped. This is the end point. But if it's Picard rank 2, you're supposed to have some contraction. And using the classification of this contractions by Mori, they studied this, in which basically was the main tool. They got the list, and they missed one family with Picard rank 5. just one, which they rediscovered in 2003, just before the
2002.
FANA conference.
2002,
2002, yeah.
September.
It was a conference in Torino called FANA conference. It was a very nice conference with the wine tasting and Barolo Castle. And they are presented this family there. So, of course, theoretically, maybe they missed something more. I don't know. But
So,
I don't.
with a little bit more why they could have discovered even more. But I mean, so that's not the point. If you go to the different fields, can you actually increase the number of the families?
No.
Why not?
I mean, it depends what you mean by families.
Maybe the group acts different.
No. Even so, okay, this is deformation family. So it depends what you mean by family. For example, you have a quartic in P4, or you have intersection of a quadric and a quartic in P1, 1, 1, 1, 1, 2, but this is essentially one family. Because here, if the quadric equation is not degenerate, it's actually isomorphic to this. But if the quadric is a cone, you get a double cover of a quadric threefold in P4, so which just looks different from that, but it's basically the same deformation family. This is the generation of that.
So wait. So if you allow,
So this is, for example, you don't even split this as two different families. It's just one family.
but if you allow singularities, some of this degeneration could coincide.
Yeah, this is also true. If you allow a singularity, so basically this deformation families, if you just compactify them, add some singular one, they can intersect. Yeah, this is true.
So particular one of this is your cubic with two singular points or something.
No. Cubics are fine.
No. I mean, isn't this
No.
this Prokhorov Kuznetsov cubic with deformation?
You mean this one?
Yeah.
No, it's Barish. I'll talk about
Okay,
this later.
okay.
It's Barish. So I hope there are no missing families, but if I later discovered one missing family, I'm also going to be happy because it's fun. I mean, if you discover something new.
No, but that's the whole point of the
I didn't hear- no.
Golish's program. That he uses these Landau-Ginzburg models. And that is the module deformation. So if you
Okay.
can classify it.
Are we recorded?
Yes.
Okay. then I will tell you during the Okay. Anyway, let me basically summarize what we did. Let me put this example. I'm going to use it. So let me summarize what we did. Again, our problem was very explicit. Singular cubic, real singular cubic threefolds. So first of all, singularities and the geometry of singular cubics studied by many people. And for example, the most recent result is a PhD thesis of Sasha Viktorova, former student of Radu Laza from Stony Brook. She's now postdoc in Europe, in Edinburgh. Basically, in her PhD, she classified all possible singularities which can appear on a cubic threefold, and but before her was also some kind of result. So basically, usually we have types of singularities, like A1, ordinary double point. Or you can like A2, or it's like basic local equation x squared plus y squared plus A2 and so on. Okay, so then let's call me S is a number of singular point. Yeah, and we consider the case when isolated singularities. And we actually non-isolated singularity we also wanted to consider after this paper, but it turned out to be that it's very simple answer there. Yeah, so most of them are rational, and couple cases we don't know.
Meaning non-isolated.
Yeah, non-isolated it actually also can be done, but we don't have it.
We did R.
We did R, but it's not yet in the paper. It is. We added, yeah. Okay, all done. But let me speak about isolated singularities, because this was the first thing. Then we added this non-isolated. But in most of this, in non-isolated case, would be rational, except I think one case when it's a singular only conic, and conic is not real. Yeah, which also appears in a paper by Kalitelen and Rutka. Okay, so isolated singularities. So
but I didn't understand the Victor's result.
she classified types of singularities obviously, which can appear, collection of singularities and so on. Okay, so let me just go case by case. So this is the number of singular points. So let me just put here. So when S is 2, we have two singular points. Then there's two cases when it's 2A1 singularities to ordinary double point, or 2A2 singularities, like that, all very minor. Yeah. In this case, it basically implicitly follows, you just have to apply a result of Benoit and Witterberg. Who generalized intermediate Jacobian technique by Philip Griffiths to non-closed field, and in this case, basically, intermediate. You can show that intermediate Jacobian of this cubic triple is not isomorph. It is a Jacobian of a curve. It is Jacobian of a plane quartic curve, but it's over C. It's not Jacobian over R. So basically, using the result, you can show that this is always irrational over C. So this is Jacobian over C. This is over C, Jacobian of a plane quartic curve. Over C. Plane quartic curve. Yeah, it's a irrational over R. It basically follows from the general theorem. They have general theorem when conic bundles over non-closed fields are irrational, in particular over R, and this just follows from the result. Yeah. Okay. In our equivariant geometry paper, we generalize the approach to equivariant setting, but over non-closed field is basically just the result. Yeah. Okay.
I apologize for the interruption, but so when you write 2 times A2, does this mean that you cannot form this A2 singularities to A1 and still be on a cubic?
Yeah.
So because if you have A2 singularity in the or the Frobenius manifold, you can always degenerate it to 2A1 singularity.
2A1?
2A2.
No. A2 you can, no. Okay. No, A3 degenerated to A1.
Well, I see. But so what is A1 then?
A1 is ordinary double point. Locally looks like this.
Yeah.
So if you put here 4, you get A3. Then it's indeed degenerate. You can smooth it to 2A1, or you can take 2A1 degenerated to, but not that one. By the way, before I proceed, let me just, before I summarize what we did, just a remark. Which rationality construction we know for cubic? Constructions we know. So one, which we're not going to use because that's obvious. So if there exists a singular point defined over the base field of a cubic defined over K, in our case R, then of course it's rational. Then of course you can project from the point and you get a birational matrix. Yeah. So basically this is kind of obvious. So because of this, we assume in our case that we don't have real singular point. So we have we assume assumption no singular points. So basically all nodes, all singular points are complex. It goes in pair complex conjugate. So it's basically mean that this is an even number. We may assume this. Goes pairs. So two pairs of complex conjugate points. Singular points. Okay, second construction. There are a few very explicit, very specific construction, which works only in some special case, but one is very general. So if you have a plane in cubic, which usually do not happen, and if you have a line in a cubic, which always happen, and if you assume that the plane and line are disjoint, then this implies, if it's defined over the base field, this implies rationality. One way of see this, you can project from the plane, you get P1, and then you can project from the line, you get P2. So composing this projection, you get a bidirectional map to P1 cross P2. Basically, that's it. So this is it. And surprisingly, this is it. We don't know other general rationality construction for singular cubes. There are some special ones which works under some special cases, like which actually not going to be applicable in the real case. But this is basically this is the only construction which we know which works a lot. So if you basically don't have a plane, you don't know how to press it for most of the cases. I actually personally think should be more construction. I think we just didn't discover it. So I'm pretty sure there should be some more construction. Yeah.
Just I'm a little bit behind, sorry. So you write there that this intermediate Jacobian over the complex numbers is a Jacobian.
It is a Jacobian of a curve.
Stream, but over the reals, there is a torsion.
Yeah, it's torsion. Not as okay, so this case is nicely done, but not by us. Then, okay, suppose now we have these two A3 singularities. Or, okay, yeah, two A3, but then there's basically two cases. So one case, we may have a plane, there exists a plane. And the second case is no plane. Yeah. If there are no plane, we basically don't know what to do, but maybe I should mention what are the abstractions. So this is a construction, and what are the abstractions? Abstractions to rationality. One abstraction to rationality, if you have real locus, if it's disconnected. This implies iteration over R. This is very nice abstraction, which is very easy to check. And in some sense, maybe it's also historical abstraction. So for surfaces, if you have a surface defined over real, if it's geometrically rational, if it's rational over C, then it's irrational if and only if real locus is disconnected. And this is by result of commutative. And actually, so for example, when I mentioned Philip result about irrationality of cubic threefold, what was the main motivation? Okay, maybe it's a question. What was your main motivation when you proved this?
What was the question?
What your theorem about smooth cubic threefold? What was the main motivation?
There was an Italian mathematician, Francesco Ghirardelli, who was visiting Berkeley.
And he was working on this question. He came out of the classic school in Italy and got us interested.
But for example, Leroy's problem, was it motivational?
Was what?
Leroy's problem, was it motivation?
No, no. It was more coming from Hodge theory.
No, I mean, but as an application, you got counterexample to Leroy. So
Yeah. So
but
that
he was not
came-
motivated by this. Okay.
But it was to understand the Hodge theory of this variety.
Okay. Okay. So this theorem, rationality of smooth cubic triples, immediately gave a counterexample to Leroy's problem. But if you want to explain Leroy's problem to say undergraduate students, the easiest way to use this abstraction, you take any cubic surface, real one, you plot it, and you see, okay, there's two pieces, it's disconnected, so it's not rational, but it's all of them are unirational. And to prove unirationality is very, very easy. So you just explicit give map, so it's okay. So what I want to say, this is very nice, powerful tools, but it doesn't work always. It works sometimes. Yeah. Okay. Second abstraction, if you have, if you resolve singularity of this threefold cubic, and if you take a Galois group, C over R, and you see how it acts on Picard, and then if you compute each one of this in the Picard resolution, so this has to be, if cubic is rational, this has to be permutation model, and this has to be zero. So if this is not zero, it implies it's irrational. So in this case, we call it, there exists like H, we call it H1 abstraction. So it also doesn't work always. But in many cases it works. Yeah. Okay. So if I have no plane, we have examples with disconnected real locus, and we explicitly gave like criteria when the locus is disconnected. So there are a lot of irrational examples, but we have a lot of examples with connected real locus, but we basically don't know. We don't know. We have no result in this case. We expect everything here should be irrational, and this brings me to another problem. This is a big problem.
Well, can I just check something? So you cannot get abstractions coming from torsion in H2 because if you have one singular point, then it's already rational.
Yeah, if you have a torsion on H6, I will see. So for cubic it doesn't exist.
Very big.
Yeah. But what I'm saying, a big problem, or maybe a big issue, that we don't know that the generation technique works over reals. We expect it, but this is absolutely open. No, the generation technique.
What do you mean by that?
Exactly what it is. So, for example, suppose I don't know what to do in this case. What I can do, I can degenerate this case. I can degenerate this family with this singular point, no plane, such that I have more singular points. And surprisingly, I get this abstraction for more singular examples. So what does it mean? It means that I take these guys, degenerate them a bit. When you degenerate, you get usually something more rational. And we get something less rational, like definitely not rational. So we may expect that very general member of this family, whatever this means, should be irrational. Over C, this is the theory. Over R, this is a big open problem which no one knows how to solve.
But so maybe it's wrong.
Or maybe it's wrong, but then no one knows how to construct a counterexample. We actually try to construct counterexample, we also fail. So this is very widely open. Maybe it is wrong, but people have to believe it's true. It should be true, but there's no proof. Okay, so basically here we don't know, but expectation.
Ignoring dimension 2, for example.
Yeah, and dimension 2 rationality problem over R is solved. You can just do case by case. But yeah. So expectation, everything is irrational here, but again, this is expectation. If there exists a plane, we have complete solution. Then rational, if and only if there exists a line in the cubic which is disjoint from the plane. So it basically means this. If you have a line in the plane, you have this construction, but in this case, it's if and only if. And basically, this is again, this is in some sense not our theorem. This is follows from Tschinkel. Or I maybe misspelled. Okay, anyway, Tschinkel. And also independent Benoit Wittenberg. So let me explain why. Suppose you have a plane. What does it mean? It means that your cubic is given by by this equation. Your plane given by x equal y equals 0 in P4, coordinates say x, y, z, t, w. You have this equation of your cubic, but then you can introduce a new variable. You can rewrite this equation as say, this is polynomial of degree 2, polynomial of degree 2, q2 over y equal p2 over x, and you call it u. And you can rewrite this equation as q2 equal yu and p2 equal xu. What is this? This is complete intersection of two quadrics in P5. And in this case, it's going to be smooth. It's easy to check. So, this is smooth complete intersection of two quadrics in P2. It's a fun. Its irrationality was studied by Brandon and Yuri, Olivier, and they proved that in this case, rationality is equivalent to existence of a line. If you have here a line defined over the base field, then it's rational, because you just take a projection from the line, you get P3. And but this map from cubic to here, it's called unprojection, because opposite map from here to cubic is just a projection from a point. This is unprojection. Okay, so in this case we just use the result and you get complete answer. Okay. Again, if you have 2A4, okay, and in this case we also suppose we have only one choice. There's no planes, and we don't know what to do. And there's two more cases when you have 2A5. So we see singularity is kind of increasing. But in this case, all irrational. All irrational. So it's very surprising. Yeah, so we don't know the answer. We know expected answer, but we don't know the answer here. We don't know the answer here. You degenerate a little bit more, and here you have homology. Yeah, so it's irrational.
So another idiotic question. Is it a problem that you can always degenerate to something that is with bigger singularity?
Yeah.
But this cannot be done clearly at variance. That's the issue.
No, you can do it over R. You can do this degeneration over R.
But I mean, how is this clear?
No, you can write down equations. You can write down
it's
equations. Yeah. And finally, the final case for 2, we have 2D4 singularities. Yeah, and so here we know that in this case there exist rational examples, explicit construction, and we have tons of there are irrational examples with disconnected real locus. Yeah, and so basically we don't have complete answer. Okay, so this is a case of two singular points. So let me check how much time do I have.
I mean, yes.
10 minutes. Is that a late? Okay, a few. Okay, so one we have only even number of singular points. So the next case is 4, and then 6 and 8 and 10. So maybe let me mention 10. first. It's not our result. This is actually was in some sense motivation to start. Then over C, such cubic is unique. 10 singular points is called Segre cubic. So it means that over R, it means it should be a form of Segre cubic. But there's a theorem by Avilov, student of Prokhorov, who basically showed that all of them are rational. So 10, we don't need 10. So what is left? That's 4. Okay, very nice case. First case, we have 4 ordinary double points. So we will have several cases. 4 ordinary double points, 4 should be, okay, 2 A1 and 2 A2. Let me put them together, or maybe 4 A2, all of them together. Okay, and another case, we have 2 A3 plus 2 A1. And okay, and one more case, 2D4 plus 2 A1. So this case is very nice. In this case, what you can do, for example, suppose you have 4A1. So your subconscious actually wants you to, in this case, Picard group over complex numbers is necessary 1. It's easy to see, basically follows Lefschetz theorem and the basic Hodge theorem. So what you can do, you can blow up these singular points. And then this is not funner, but it's almost funner. Why? Because if you have those 4 singular points, you have 6 lines, they form a tetrahedra, you have 6 lines passing through them. And then they intersect with anti-canonical divisor by 0. So this is the only curve which intersects with Mansky by 0. So it's almost funner, but then you can flop this curve. And you get something. And then the 4 points contained in a hyperplane. This hyperplane is a singular cubic surface. When you, with 4 nodes, it's called Clebsch cubic surface. When you blow up, you resolve singularity. When you do flop, you actually contract them. So you got a P2 with a normal bundle of 1. So you can contract it. And when you contract it, and you get, this is Prokhorov-Kuznetsov form of a divisor in, let me put it, P1 to the 4th. But this form is actually contained in the product of two real surfaces, into product of 2 spheres in P3 cross P3. So this is form of P1 cross P1, and this, as he is a divisor of degree 1, 1, and he is a divisor of degree 1, 1, 1, 1, 1. So this is basically this Prokhorov-Kuznetsov example which I mentioned. They put conjecture in the paper that over non-closed field, if Picard rank of this is Z, they expect it to be irrational. In our case, Picard rank is Z plus Z. It's exactly what Neil asked, this Z2 action, because it's the lower group of Z2. We actually don't know what to expect here. I actually expected probably irrational, but we cannot.
I think you're right.
Yeah, okay, but again, we don't know how to prove it. Yeah, okay. So this contraction works in all these cases. So we have this. But we don't know what to do next. If we use the generation technique, if we believe in the generation technique, then we can show, then very general should be irrational. We can,
or the real.
if we believe the generation technique over reals. But this is, we don't know. Yeah. Okay. In this case, we have 2 subcases. So we can have one real plane. And then in this case, all of them are rational, all rational. Or we have 3 real planes. In this case, we have a rational example, and we have an irrational example. So both. Yes, and in this case, we have actually a very nice criterion. So it's rational if and only if there exist 3 planes in the cubic plane, of course, in the cubic. So there exist 3 planes in the cubic. Okay, and basically we have two more cases left. When we have 8 singular points, it's very similar here. This is the generation of that. So it's in 8 singular points, it's rational if and only if it contains 3 planes. And when it's 6 singular points, again, if it's we have several cases. If okay, let me mention it, then I stop. So this is the last case. So we have, as I said, 8. It's 8 rational if and only if contains 3 planes. If it's 6 singular points, so we have 6A1 and without planes. With one plane, with a real plane, with a plane. In this case, always rational. Yeah. Then if we have 6A1, no planes, then it's rational if and only if X3 contains a real cubic scroll. Again, this is if and only if. It's very clear geometric condition. Yeah. And okay, this is one plane. And then we can have 6A1 with 3 planes. Again, we have examples. There exists irrational example, there exists rational examples, but we don't know the answer in general. And all remaining cases, there's some remaining list of singularities, all rational. Okay. So basically, we didn't solve the problem completely, but in each case, we don't know the answer. We have some expectation, and we have cases very explicit. We put normal forms very explicitly, so and the examples with the connected real logs, disconnected. So, okay, so basically, that's what we did.